Yeah, hello, I'm Leo. So I was asked to change the slides to because originally assumed that I'll be able to use my laptop here. So the slides aren't perfect, but I'll try to make up for it. So the idea is, how do you JIT Rust, and why use JIT anyway, right? So most code you write doesn't need JIT. So this wouldn't apply to most people here, but some people here, like the ones who is doing GPU programming or other like low-level high performance stuff, this might apply to. So JIT is useful for any kind of dynamic algorithms. Let's say you have like an SQL database and you need to do arbitrary querying logic really quickly. That's a dynamic kind of a thing. And then you have console emulator. So let's say you want to write a DS emulator or something. You can't do modern consoles without using a JIT at all. And basically, yeah, anything that's highly dynamic would require JITting. Actually, a question. So, asking the room. Basically, who here is familiar with LLVM? Okay, good. And who is familiar with linking and like why linking binaries is necessary, why Rust does it, and so on? Okay, sounds good. Yeah, so JIT case study. An example is, of course, Postgres, which is an SQL server. So they not recently, I think it was like more than 5 years ago, but they transitioned to using LLVM to accelerate their queries. So previously they would have they call it the volcano-style iterative model, where they chain things together, and each chain adds an extra dispatch or a condition, and that's slow. And then the idea is that what if we combine all those chains into one precompiled function at runtime to make it faster, and it did make things faster. I can't show you their exact process, but the idea was they compiled C code into LLVM and then compiled the LLVM into C++ code that invokes LLVM. It was very complex. But yeah, so I was thinking, I was actually on this problem for over 2 years now. I originally started making my own DSL that compiles, that has similar to Rust syntax and compiles to LLVM, but that didn't go too far because I'd make my own programming language. The idea was, how do I make JIT that can do high-level concepts, because I don't want to re-implement a vec or a hash map or any other stuff that already exists out there. So kind of just JIT Rust. And the idea, technically yes. And over a lot of trial and error, I came up with the approach that Postgres does, where you convert Rust to LLVM, and then you link the compiled LLVM that was generated by Rust at runtime using your own manipulated functions. So you do need to directly interact with LLVM, so it's not pure Rust JIT, but it still saves you a lot of time. So what's the process? Yeah, firstly, convert Rust to LLVM, then you join those precompiled functions at runtime, and then you cry because LLVM is absolutely miserable. If anyone who's touched LLVM, you know how miserable it is. I'll probably rant about it more later, and then you run the JIT code and you profit. So step one, yeah, easy. You convert Rust to LLVM IR. This is very simple with Rust because you can just do --emit LLVM BC, which is the machine readable version of IR, which is it's faster for your computer to pass afterwards. Of course, LLVM IR also works if you want to read it yourself, but yeah. It compiles each individual Rust crate and module, not module, just the crates, each individual crate to its own IR. And here's what it looks like in your deps folder. So if you use the command flag, you get these extra files in your deps folder, which represent each crate and its bytecode. So here's an example of the transformation creates. Oh, by the way, I was going to mention the case study, the dummy case study that will be going through. I was planning to show it on my laptop, but I guess I'm going to explain it. So the idea is, imagine a small array of users. Each user has random fields, arbitrary fields, not arbitrary fields, but a set list of fields. But you have arbitrary filters. You have filters that query an arbitrary field, and then you have logic for the filter. For example, filter starts with, filter ends with, filter includes string, and so on. So a couple of those filters. And you can join these filters together with and or. So basically, you have a composite filter on strings on arbitrary fields with arbitrary matching logic. And yeah, here's an example of a function within the that it precompiles for me that fetches a string for the phone number of the user. Yeah, and sorry, you can see this is the top one is the Rust one, the bottom one is the LLVM, and it basically does a couple querying fields from inside of LLVM and returning the string. But when you look at the LLVM IR that's generated for this crate, you'll see that there's undeclared functions. These functions, can I use the cursor? Yes, I can. So yeah, it's kind of hard to read what this says, but you can kind of see core, panic, or like alloc, string, and so on. So these are functions from other crates. In this case, core and alloc, and potentially any other crate you import. So I asked about linking earlier, but the idea of linking is in Rust, Rust doesn't compile your entire program at once. It compiles each crate individually, and then it links them together using existing linkers that also work on C and C++ into one executable afterwards. There's a bit more logic of it because of generics work a bit weird. But yeah, the general principle is Rust compiles the functions for each crate, and then it links the functions together afterwards. And that's why like inlining is a weird thing across crate boundaries and so on. But yeah, anyway, so we need to link things in order for this to be useful at all. So we link them all together. It is harder than it sounded. I wrote a huge, not a huge, but like a relatively lengthy Rust script in order to do the linking by using LLVM invocations and some other stuff. But it basically, it takes, starting with the main crate, it takes all the like dependencies and links them in by managing private and public stuff. It then optimizes it all together using LLVM optimization. LLVM is very, very powerful at optimizing your code. You'd be very surprised. But yeah, so it joins them all into one single file. But then another issue you see is that there's still functions missing. These functions would still be missing in this case because core and alloc are not precompiled for you. You need to separately compile core and alloc into LLVM bytecode as well. So that's where this nightly option comes in. You do build std core and alloc as well. Still more undeclared functions. But these functions we can ignore for now because they are only really needed at runtime. So basically just the allocator functions and panicking. There's like only about 7 of them, and they're very simple. And of course, yeah, we optimize it, I mentioned earlier, but optimizing helps a lot because private stuff gets inlined. You can control what inlining does, like what you need, what you want to be inlined, what you want to be removed. You can have pretty strong control over that stuff using Rust directly, and then look at what kind of LLVM it creates afterwards. So finally, step 2, we have importing these functions and joining them together. So this is a part, you don't need to read everything, but the idea is you can see how there are different labels. So here is like blocks, labeled blocks, or middle 1, because this is a bunch of or instructions. I mentioned earlier there's composite filters. So there's and or and some other things. It requires conditions. So you can see here like we have call separate string. So I basically inject a string into LLVM IR, and it converts it to a Rust str reference using this precompiled function. Then I have get user field first name, gets the first name, and then check if the first name starts with the injected string, and then starts with is the Boolean, and then if starts with jump to success because it's I think it was an or, and then if otherwise jump to or middle. And then it keeps going from there, like over and over again until it reaches either the fail block or the success block. And yeah, very important thing to consider though. The Rust ABI is not stable, and sometimes it can act in very unexpected ways. So when I say you need to compile Rust to LLVM and then join those functions together, you do need to interact with the LLVM versions of the Rust functions, and they can compile in unexpected ways. For example, here you're returning a vec, but under the hood, Rust actually converts this to a pointer argument that you then write to, rather than returning it. I removed a lot of attributes here, but yeah, it makes sense why this happens. You just need to pay close attention. Personally, I just use pointers for everything because pointers usually get optimized away anyway, especially within when you join functions together. But yeah. Well, step 3, misery. Basically, LLVM is a huge pain, and yeah, I love spending an entire week asking questions on the LLVM Discord server for them to be answered at 4 a.m. every night, and eventually getting it working. A lot of their documentation is awful, and they're in the middle of transitioning from different JIT engines, and it was a pain. But it's all working, and I have a GitHub repository, which I did not link to in my slides because I forgot to because I was changing my slides. But you can ask me for the GitHub repository later, which has an entirely functional version of this with comments and descriptions and the slides. And step 4, running it. So using org.jit, which is the new one, and it's seamless, it works. And profit, it runs at half the speed, like twice as fast in this simple example. Of course, this example is very simple because at runtime, it can probably do a lot of branch prediction, among other things, much easier. But if you're doing something like a JIT, you're going to have magnitudes of performance difference with a JIT. So yeah, if you're doing something like an emulator, where you're emulating a different byte code or something, yeah, you're going to have magnitudes of performance difference. So bonus, making an emulator. I will not go into this too much, but I recently tried to make a project where I emulated a 6502, which is the same processor that powered the NES, among other things. And yeah, so I had this big opcode macro, which internally calls the emulator function. So the emulator, it can take in a bytecode instruction to just execute on the spot, and it is no STD. By the way, I forgot to mention, but anything no STD can compile. You can import the regex crate. You can import any crate that's no STD, and it should be able, in theory, compile to this just fine. Yeah, so here I have my emulator, which is no STD, and here this macro lets me call any bytecode thing, and then you can see here me calling this, basically generating a new function for each opcode, which is very spooky looking, but in the end it generates a pre-optimized function for every single possible opcode. And here's the generated IR for one of the opcodes. In this case, it's a no-op instruction, so it's pretty small. It just increments the program counter, it does nothing else really. But yeah, it's just an example function. And then I build the functions together. So for example, this is a group of instructions starting from this pointer in 6502 memory, and it goes to the jump head, but then each block is like a different instruction in the 6502. And of course, I have the jump pad because you can exit the JIT at any time and then resume. And this is like the resuming jump pad where it can resume back to any instruction that it missed. Or for example, if you jump from one block to another block, it goes straight to the jump pad as well. And when you optimize it, you'll be surprised with how much LLVM does. As I said before, it optimizes so much. And I guess I don't really have a flash demo for this, but at the same time, yeah, when it comes to JITting, it's just, yeah, I don't know. I think I explained everything. Any questions? Yeah, I guess another thing I'll say is another use case I was coming up with, which slightly is relevant to a previous talk, but the audio one. So I made an audio synthesizer, but it is, I want it to be as fast as possible, but then I realized that to be able to render very complex audio pipelines as fast as possible, you need to have to JIT it, because currently I JIT a pre-compiled subset. I pre-compile a subset of possible functions, possible pipelines, like different effects, different kind of stuff that a audio voice can do. But in the future, I might be able to JIT it as well and be able to have the most fastest possible voice at runtime, depending on the configuration. But yeah, any questions? It's too niche, I guess.
No, that's one question. I was like, why? Everybody is like always like, why? What drew you this passion like thing?
Right. Yeah. Well, I mentioned I have been thinking about this for over 2 years, but the idea is, oh yeah, why is this area of computing not as accessible as it should be? Because again, like Postgres had to jump through so many hoops in order to implement their JIT, and it's very hard to make a competing database to Postgres because you can't beat Postgres without a JIT, among other things. I mean, like many other programs which would benefit from a JIT because of dynamic execution, but it's very, very, very hard to do. So I was trying to come up with the most ergonomic solution I could, and this is my final solution after 2 years of thinking.
When I think of just-in-time, I'm kind of thinking like Java.NET, and they kind of do sort of lots of magic things like if it's, well, I don't know exactly how it works, but like if it works out you're calling a virtual function with the same type over and over again, it'll compile a special version of that function. And do things like that, fancy stuff like that. Does LLVM do any of that? I've never heard of it. I've heard of LLVM, but as a JIT thing, or is it just sort of you just give them code that you can compile and link it to your program at runtime?
Yeah. So, oh, sorry. Yeah. The idea here is we already have plenty of languages that do JITting, but of course, like it's hard to make your own language. But TLDR, when it comes to JITting, to have a properly performant application, you need to be able to control exactly what the JIT does, exactly the kind of function it generates. So with Java, and JavaScript for that matter, or any other JIT language, it does a lot of runtime assumptions and guessing based on performance metrics and like what each function probably does. Like it kind of makes estimations of what each function might likely do in order to do the best optimization. But ideally, you should be able to make that optimization, like that assumption yourself, because you know better what a function does than what the runtime does. So because of that, the idea of LLVM is so the whole point of LLVM is you have the intermediate representation, the LLVM IR, and it converts it to any bytecode, convert it to x86, ARM, WASM, whatever. And so it's just direct, IR to bytecode conversion. No assumptions under the hood, nothing at runtime. You just call the function afterwards as if it's a native function. But you can compile any native function you want with the exact performance or like the exact characteristics you want because you know best what you want to happen at runtime exactly, rather than having a runtime assume it for you.
So just one more curious question: that what's next? What's your like goal, or was this like just an experiment? Let's crack it, you know?
The goal here was to share my progress and have a working demo, which is in the GitHub repository, which I can link to you if you ask me because it's not in the slides. But actually, can I tab into the URL so that they can see it later? Oh, yeah. Of course. Just a web browser. I will send it in Discord later, but yep, Arduino GitHub, and surely it is the first result. There we go. It's pretty slow. Maybe Wi-Fi here. But how do I check show activity? Oh, JIT demo right there. So it is a pretty well documented in terms of like actually running it and like what each part of the project does repository. So if you want to replicate these results yourself, there should be instructions here, including how to compile LLVM, which is actually harder than it sounds. But yeah, so what's next to this project? I will keep trying to find applications for it and maybe try to find more ergonomic ways of approaching it, because whatever I did here is not the most ergonomic way. But hopefully in the future, more like tailored JITs where you have full control over what is generated will be possible in Rust, or like a subset of Rust compared to what is available now. Yeah, go for it.
Just to follow up on that question, you've recently said that you know what you want, like to be JIT, but I don't know. So how do you know what I'm looking for to get your JIT to make something faster? That's like the thing is not clicking for me. Yeah.
Right. So the idea is, how do we minimize the amount of LLVM you have to use in order to JIT something? So like, for example, I don't want to re-implement a vec inside of LLVM or a hash map or any of that. So we already have Rust implementing that. How do we reuse what Rust already generates in order to, while still having the exact same performance? So yeah, basically, you can take any Rust code that does whatever you want already and get it to compile to LLVM, and then use that Rust code inside of LLVM and then run optimization passes. LLVM optimizes away a lot, and then you have JITted code that does exactly what you want, but it does exactly what you want without any extra if conditions, without any extra like dynamic dispatch or any of that, because you pre-compiled it right then and then. So like again, if you have, let's say, a Postgres query at runtime. Like again, you have a Postgres query that filters by the word hello inside of some field. You don't need to say ask which field is this, query the field, to ask like if it's equal to this string. You can pre-compile it to say query this specific field already and compare it to this specific string already, and then run that function at runtime, which will run much faster than for each field doing dispatch.
Yeah, really good job with this. Thank you.
can you put it all into a proc macro that I just have to put on my functions?
Sorry,
And can you just put it all into a proc macro that I can just put on my function to be like, just compile it?
Well, at the moment, no, because basically the idea is you need a no-std crate that compiles to Rust. So compiles to LLVM IR. And then at the same time, you need to be able to join those functions at runtime somehow. And for that, at the moment, you have to directly interact with the LLVM. And of course, you need to be aware of the ABI. For example, I mentioned all the issues with the ABI where it can do unexpected things. So you need to like have full awareness of everything that goes on in order to do it 100% correctly. In the future, maybe it will be possible. The idea is that, yeah, I want to be able to pre-compile pipeline. So you like specify a pipeline of what you want to join together and just say compile and optimize. And then we'll give you the most optimal one.